A very good morning to Dr. Azwan. Today, me and my group will be presenting about passive cooling system design and optimization. This group comprises of 4 people, so this is our team for this project. For this project, the main focus is on thermal management in modern electronic systems. Nowadays, electronic chips are becoming smaller and more compact, but at the same time, they generate more heat during operation. If this heat is not removed properly, it can cause problems such as thermal throttling, reduced performance instability, and even failure of electronic component. To solve this problem, a passive heat sink is used. A passive heat sink does not require external power such as a fan to operate. Instead, heat is transferred from the electronic chip to the heat sink through conduction. After that, the heat is released from the fins of the heatsink to the surrounding air through natural convection. This project focuses on designing and optimizing a passive cooling heatsink for an industrial electronic chip. The aim is to improve heat dissipation while keeping the design simple, reliable, and suitable for natural convection cooling. There are 6 main objectives for this project, which is to analyze the thermal performance of a passive heat sink using conduction and natural convection principles. Next is to calculate fin efficiency, effective surface area, thermal resistance, and chip operating temperature using manual calculation. The third is to validate the theoretical results using SolidWorks flow simulation. Next is to conduct a parametric study by modifying the heat sink fin geometry. Next is to compare different fin configurations based on temperature reduction and airflow performance. Last but not least is to identify the most efficient heat sink design while reducing the unnecessary material usage. This slide summarizes the key findings from the literature review related to passive heat sink cooling. Based on previous studies, thermal management is very important because modern electronic devices generate high heat due to compact chip sizes and high power density. If heat is not properly dissipated, it can lead to performance degradation and component failure. The literature also shows that passive heat sinks are commonly used because they do not require external power. Heat is transferred from the chip to the heatsink through conduction and then released to the surrounding air by natural convection. This makes passive cooling suitable for systems where silent operation, reliability, low maintenance, and low power consumption are important. Another important point from this literature is the role of fin geometry. Fin height, thickness, spacing, and number of fins strongly affect the heat transfer performance. Increasing the surface area can improve cooling, but very small fin spacing may restrict airflow and reduce natural convection efficiency. Material selections is also important. Aluminum alloys are widely used for heat sinks because they have good thermal conductivity, are lightweight, corrosion resistant, and easy to manufacture. Finally, studies also highlight the use of CFD simulation tools, such as SolidWorks flow simulation, to analyze temperature, distribution, velocity profiles, and airflow movement. This supports the validation of manual calculations and helps to optimize the heat sink design. This slide shows the main specifications and design requirements used for the heatsink analysis. The heatsink is designed for a 10-watt electronic chip operating under natural convection cooling, which means there is no fan or external cooling device involved. The base area of the heatsink is 60 millimeters by 60 millimeters with a base thickness of 5 millimeters. This design uses rectangular fins with a total of 10 fins. Each fin has a thickness of 2 millimeters and a height of 30 millimeters. The chip material is silicon, while the selected heatsink material is aluminum alloy 6061. Aluminium alloy 6061 is selected because it has good thermal conductivity, is lightweight and has good corrosion resistance, and is easy to manufacture. These properties make it suitable for passive cooling applications. The system is designed to operate in an ambient temperature of 30 degrees Celsius, and the maximum allowable chip temperature is 85 degrees Celsius. Therefore, the heat sink must be able to transfer heat efficiently from the chip to the surrounding air while maintaining a compact size. The main design objective is to reduce the chip temperature, improve heat dissipation, and ensure reliable operation without using active cooling devices.
Good day, doctor. My name is Sugashni and my matric number is CD230133, and today I will be presenting my part of this project, which is phase 1 theoretical analysis, also known as the base calculation. In this phase, manual heat transfer calculations are carried out to evaluate the thermal performance of the proposed heat sink before performing any simulation. The purpose of this calculation is to determine whether the initial heat sink design is capable of maintaining the electronic chip below the maximum allowable operation temperature. So in this methodology, the phase 1 is focuses on the theoretical analysis using manual calculation based on the principles of heat conduction and natural convection. Before starting the calculation, the heat sink geometry and operating conditions are first defined. As also shown in the diagram, the proposed heatsink consists of 10 rectangular fins mounted on an aluminum base. The base dimensions are 60 meters by 60 meters with a base thickness 5 millimeter. Each fin has a thickness of 2 millimeter and the height or corrected fin length of 30 millimeter. The heatsink material selected is aluminum alloy 6061, which has the thermal conductivity of 170 watt per meter Kelvin because of its efficient thermal conductivity, lightweight properties, and corrosion resistance. The electronic chip produces a heat load of 10 watts while the surrounding ambient temperature is 30 degrees Celsius. Since the cooling method is natural convection, the heat transfer coefficient used to 8 watt per meter square Kelvin. These parameters serve as the input data for all the theoretical calculation presented in the following slides. The first calculation performed is the fin efficiency calculation. Fin efficiency represents how effectively the heat sink fin transfer heat from the base to the surrounding air. First, the fin parameter M is calculated using the convection coefficient, thermal conductivity, and fin thickness. After substituting all design values into the equation, the value of M is obtained as 6.86 per meter. Next, this value is multiplied by the corrected fin length, giving MLC equal to 0.2058. Finally, this value is substituted into the fin efficiency equation. The calculated fin efficiency is 0.9861 or approximately 98.6%. This result indicates that the fins are highly efficient, meaning almost the entire fin surface is effectively used for heat transfer. Therefore, the selected fin dimensions are suitable for dissipating heat through natural convection. After determining the fin efficiency, the next step is to calculate the effective heat transfer area. First, the base area is calculated using the base dimension, giving an area of 0.036 square meter. Then the surface area is one fin is calculated. Since the heat sinks consists of 10 fins, the total fin area is multiplied by the number of fins and corrected using the previous calculated fin efficiency. After adding the base area, the total effective heat transfer becomes 0.0391 square meters. So the next convection resistance is calculated. This resistance represents how easily heat is transferred from the heat sink surface to the surrounding air. The calculated convection resistance is 3.1969 degrees Celsius per watt. The conduction resistance is then calculated, which represents heat flow through the aluminum base. Because aluminum base has a high thermal conductivity, the conduction resistance is very small, with value of only 0.00817 degrees Celsius per watt. From this result, we can conclude that the major thermal resistance comes from natural convection rather than heat conduction through the aluminum material. In the final slide of the manual calculation, the operating temperature of the electronic chip is calculated. The chip temperature is determined by adding the ambient temperature to the temperature rise caused by the total thermal resistance. The total thermal resistance is obtained by adding the convection resistance and the conduction resistance. After substituting all the calculated values into the equation, the final chip temperature is 62.05 degrees Celsius. The final calculated results are fin efficiency is 0.9861, effective surface area is 0.03191 square meters, convection resistance is 3.1967 degrees Celsius per watt, conduction resistance is 0.00817 degrees Celsius per watt, and the calculated chip temperature is 62.05 degrees Celsius. Since the temperature is well below the maximum allowable chip temperature of 85 degrees Celsius, the proposed heat sink design satisfies the thermal requirement under the base case. Therefore, the manual calculation confirmed that the design is theoretically acceptable and is ready to validate using SolidWorks flow simulation in phase 2.
In phase 2, SolidWorks flow simulation was used to validate the manual calculation results from phase 1. The purpose of this study simulation is to study the actual thermal behavior of the base case heat sink under natural convection condition. This base case model consists of 10 straight rectangular fins mounted on an aluminium base with a size of 60 mm by 60 mm by 5 mm. Each fin has a thickness of 2 mm and a height of 30 mm. From the simulation results, the highest temperature occurs at the chip and heat sink interface. This is expected because the chip is the main heat generation area. The heat then spreads through the aluminum base and fins by conduction. After that, heat is released from the fin surfaces to the surrounding air through natural convection. The airflow result shows buoyancy-driven natural convection. This means hot air rises between the fin channels while cool air enters from the surrounding region. This airflow movement helps to remove heat from the heat sink surface. The simulation reached a steady state maximum chip temperature of about 91.5 degrees Celsius. However, this value is higher than the allowable limit of 85 degrees Celsius. Therefore, the base case heat design is not sufficient and further optimization is required in the next phase to improve the cooling performance.
Hi, my name is Trishan. This is our first iteration that I would like to explain. We use 60 times 60 times 5 mm cross calculate heat sink with 10 fin, 2 mm thick, 30 mm height. Material is 6061. Heat source is 15 watt. Ambient is 30 Celsius. We mold in SolidWorks and ran thermal simulation. Result shows heat spread well through the base and fin with no hot spot. The coverage plot confirms steady state was reached. Next, I would like to present the iteration 2. For this iteration, the overall dimension remains the same with base of 60 mm by 60 mm and a thickness of 5 mm. The heat sink used 10 fin with a fin thickness of 2 mm and a fin height of 30 mm. The heat source is maintained at 15 watts while ambient temperature is 30 Celsius. Aluminium alloy 60 by 60 is selected as the heat sink material due to its excellent thermal conductivity and lightweight characteristic. The main improvement in iteration 2 is the fin geometry compared to iteration 1. The fin are redesigned with a smoother and more streamlined profile. This modification is intended to improve airflow between the fins and enhance dissipation efficiency. The 3D model was developed and analyzed using SolidWorks simulation. Thermal analysis was conducted to evaluate the temperature distribution and overall cooling performance of the new design. This iteration aims to achieve lower operating temperature and better thermal management while maintaining the thermal and same size of the material constraint. Overall, iteration 2 demonstrates an optimized fin structure that has the potential to provide improvement heat transfer performance compared to the previous design. Hi, next I would like to explain the iteration 3. We changed the fin type to radial fin to improve more omnidirectional airflow. Base is 60 by 60 by 5 mm with 10 fin, 2 mm thick, 30 mm high. Material is aluminium 6061. Heat source is 15 watt from a silicon chip ambient at 30 Celsius to 303 Kelvin. Besides that, the thermal simulation run compared this radial against previous cross fin cut. We expected performance in natural convection due to the radial layout. Besides that, radial fin improved airflow from all directions with the specification of 60 by 65 mm base, 10 fin, 2 mm, 30 mm aluminium 60 by 60. By setup 50 watt silicon chip 30 ambient with a model of 109.9 gram built in SolidWorks. As well, the thermal simulation and the simulation is better compared to the iteration 1 and 2. Thank you. For iteration 4, we went with the school star-shaped design called radial plate fill. Why? Because heat can escape in every direction like a disco ball. It's 60 by 60 mm, pretty small with a 10 fin striking up, made from aluminium 6061, lightly cheap and cool things fast. We are pumping 15 watts of heat into it, same as a hot laptop chip. Air around it is 30 Celsius. We built this 3D model in SolidWorks. Total weight only 110 grams, lighter than our phone. Next, we all test it and see this star design beats our old one, and it works. So compared to the previous 3 iterations, this iteration gives us a good result and creates a heat spot, and it is steady state. Thank you.
Assalamu alaikum and hello everyone. My name is Tawassul Muhammad and I will demonstrate the result and also the conclusion of our project. So as we saw from the report and my friends' presentations, we can say that the simulation showed that the fine geometry strongly affected the heat sink performance, and also knowing the natural convection is the main cooling mechanism in passive heat sinks. Also the effective cooling depends on both heat transfer and also the airflow pathways. Knowing that the airflow obstruction can reduce heat dissipation even if surface area is increased. Also, an optimum balance between the fine spacing and airflow is essential. Knowing that the barometric study showed that the fine geometry greatly affected the heat sink performance, and that zigzag plane fine provided the best cooling because it increased heat transfer area while allowing good airflow. Knowing that also the cross-cut and radial plate fine designs performed poorly because they restricted the natural convection airflow. Knowing that also the increasing of the fine thickness improve the heat convection but reducing the airflow between fines, resulting this this resulting in only a small improvement and overall effectiveness. Passive cooling requires an optimal balance between surface area, fine spacing, and airflow accessibility. This graph here, it's a comparison between the thermal performance of different heat sink configuration, and the horizontal axis represented the design configuration, while the vertical axis is representing the maximum chip temperature. Since the objective of this project is to improve the cooling, so a lower temperature indicates better thermal performance. Assalamu alaikum, my name is Tawassul Muhammad, and I will demonstrate the result and the conclusion of our project. So as we saw in the report, the CFD simulation showed that the geometry strongly affected the heatsink performance, and also the natural convection is the main cooling mechanism in passive heat sinks. It's a fact, and also the effective cooling depends on both heat transfer and also the airflow of the pathways. Also, the airflow obstruction can hit. Why?